Thank you, ma. Oh, good morning, Dr. Taiwo.
Yeah, good morning, Dr. Lawal.
Yes, sir. Yes, sir.
Good morning.
Yes.
Káàárọ̀, ẹ ṣeun o.
I can't remember.
Ẹ kú iṣẹ́. Thanks so
Yes,
much.
ma'am. Thank you, ma'am.
Good morning. As announced on the WhatsApp platform, names like BOA that just saw now will be removed if by the time the class starts. So please kindly rename your devices as appropriate. It's just click on your name and rename it.
It's Toby around. It's Toby there. Okay. Toby, are you there?
I'm not here, ma. Good morning, ma.
You're not there.
I was exited, but I was just at the boo. I was saying I had to reclaim host, so I could
Okay.
speak. Yes.
Can you create a waiting room, please?
Done that already.
All right. Thank you.
Yes.
Okay, dear.
Yeah. Prof,
Yes.
just just an observation, ma. So some people were, if they are removed from meetings, they will not be able to have access to it.
I know.
No.
It's a normal thing. Once they're removed, they're treated as hackers.
Okay, yeah.
But anybody using a Zoom should know it's a risk. And so if they don't label the device, they can't come in.
Coming, yeah.
It's a
And
normal. Once you're removed, you're treated as an hacker. So,
yeah.
so I mean, if you've been using Zoom, you know you can't come in without naming your device. And then this class is large. The risk is just too high.
Too high, yeah.
I can't. Yeah. So
And we also
it's
have
a
people
norm. It's a
joining
Zoom
on
attendance
YouTube.
norm. They should know. And they can go join on YouTube. So there's nothing abnormal about not letting people who don't label their device come in.
Yeah, sure.
Yeah.
So
Yeah. So all right.
I need to give Professor Lawal access.
Okay. Thanks for managing this.
No problem, ma'am.
Grateful.
No problem. That's all.
Like this boy now.
Most likely Bank of,
Or is BOA a full name?
Agriculture.
At least boy ahead now when you are telling them to name the device and hasn't named it. Now you eject the person is a risk. You can't come back in. And it's disturbing because I can't admit all, which I should otherwise do in his absence. I mean, it's nothing new. It's a practice of years. Do not people start come and act.
Let me send message to waiting. Okay, you already sent message to waiting room.
No, please send a message to the waiting room that they should please name their device. It's only Boal that is left there.
Yes. By 8, if he or she has not renamed, we have to remove them.
Yeah, because it's disturbing the admission process. You're very right. If that 8 is not there, we'll just remove it so that I can admit properly. We'll go to YouTube.
Toby,
I think he's
is
left.
Toby still there?
Yes,
Okay.
yes, Professor.
Okay, yeah. So there are some names that I will admit, and within 1 or 2 minutes, they reappear in waiting room. Can you explain what's happening?
They are doing two devices.
Or
It's
they
either
Uh,
have
they're doing
bad
two
network. Yeah,
or they are dropping.
yeah.
It's either they're dropping or they come in with two devices.
okay, I think the person named Boa is chatting me up. He or she said she has renamed his device and is still in the waiting room, but what is appearing here is not renamed.
And please, maybe you take the
Okay,
person through, guide the person on how to
okay,
rename. Uh,
okay, yeah, he's a person, he's the one. So what I'll do is I would admit I'll go and help him rename.
you can help the person rename.
Yes,
Yes,
that's what I
Prof.
want. Yes, I
Yes.
can. That's what I want to do now.
Okay, then. All right.
Yeah.
Thank you.
I've admitted I can't find him.
Do a search.
Yeah, that's what I
Maybe
want.
it has been renamed. Maybe the
Okay,
rename has
maybe.
not shown.
Okay,
Uh,
Boy is in waiting room.
he's still there. He's still in
I
the
will
waiting
admit.
room.
I will admit now and then rename. Yeah.
Okay,
okay,
thank you.
First of all, please
okay. Yeah,
name.
I'll rename now.
All right, great.
All right.
Morning, everyone. Thanks for being here again. Very much thank you to my very own Professor Alani Tayo. It's another exciting 2 hours of statistics, and believe me, I'm supposed to be at a very big meeting. I just took away my 2 hours. Every time I sit under this lecture, there's always something peculiarly new to learn. Fundamentals basic. Thank you so much once again for giving us your time. We do appreciate it. Please note, everyone, that for this, because of the large number of classes, we would not open the space for you to ask your questions directly. Please put all your questions in the chat box. We treat as much as we can immediately after the lecture. But if there's anything that is outstanding, please take it to the platform. Please try to keep your mic muted throughout. And if your devices are not named, please name your devices. We'll immediately chuck out anybody whose device is not named. On that note, I want to hand over to my very own Professor Taiwo to please go ahead with this lecture. Thank you very much, sir.
Many thanks, Ma, and thank you for the honor and thank you for the opportunity. Good morning, everyone. I will just be sharing my slides now. 1 minute, please. Uh-oh. Please, 1 more minute. I think I mistakenly closed my presentation. Let me just open and reshare. Just a minute, please.
It's fine, sir. Thank you, sir.
Yeah. Dr. Lawal. Dr. Lawal?
Yes. Should I share from my hand?
No, I'm getting a message saying that my screen sharing is paused. What does that mean?
Okay, let me check. Just a minute.
It's paused.
Yeah.
Jeez.
Can you retry now?
Or we can see it.
Can I do what?
Okay, it's already showing on the screen.
Okay.
It's just for you to make it full screen. We can see it.
Funny enough, on my own side, I'm not seeing anything. Let me just, I'm coming.
Maybe you should just stop sharing and reshare.
Okay, let me try that.
Okay. Technology can sometimes be like that. We can see it on our own end now.
Is it full screen or still partial?
It's full screen now.
Okay, I think I'm good to go. I apologize for that little hitch.
All right.
Yeah, so once again, good morning, everyone, and welcome to the second lecture on our quantitative data analysis series. This morning, we'll be talking on correlation and chi-square test. And maybe before I continue, Dr. Lawal, when you see that I'm getting or running short of time, like you did last week, I will appreciate maybe you just buzz me so that I can know how to manage my time very well. All right, so my name is Nii Taiwo, and like I did say last week, this presentation contains some materials that are adapted, reference from different online sources, and they are included solely for educational and informational purposes. I don't claim ownership or original authorship of the content source from these external references. Full credit is due to the respective authors and creators of this work. So I started last week with just a recap of what the research process is, starting from the research topic, the research title, the research question, and just going down the process to literature review, to the different hypotheses that you must have generated, the approach you intend to do or to take for the study, the sample size that you've calculated, how you selected the sample, and last week we spoke about variables and the measurement scale, and we are going to just touch over them in a slide or so, and data collection down to data analysis, which is the focus of these 4 weeks of lecture, after which you can then present your reports and make a presentation. So last class, we defined a variable as a characteristic that may assume more than one set of values to which a numerical measure can be assigned. And we said that variable is a characteristic that changes, that means it alters, it's not a constant. A constant does not change, but remains the same. And last week, we also said that there are 2 types of variables. We have the quantitative variable, and then we have the qualitative variable. The quantitative variable can be continuous or discrete. We said continuous variable is one that can assume an infinite number of values. And another word is just that it's something that can be in fractions, something that you can measure with decimal points. And the discrete values variables are the ones that are whole numbers, the one that you can count. So this one is what you can count. The continuous is what you can measure, but they are both quantitative. On the other side, we said qualitative variables are also called categorical variables. It can be ordinal in a situation where you can arrange them either in ascending or descending orders, or it can be nominal, where it's just a label to describe a category. Then we spoke about measurement scale because these are cardinal foundation for us to understand before we can actually go on to data analysis. Measurement scales are the scales we use to quantify or give numeric value to variables. We have seen variables. So when you give them numbers or values, we call that measurement scale. And there are 4 types. We have the nominal scale, the ordinal scale, the interval scale, and the ratio scale. And last week, we emphasized that these 2 are for qualitative variables, while these 2 are for quantitative variables. And I said this is the one that is mostly used, for quantitative variables because it has, a definite and an absolute 0. And we said that the nominal variable is the weakest, followed by the ordinal variable, and then the interval variable. The strongest variable is the ratio scale that has an absolute 0. And we went on to talk about data. By the way, the moment you measure a variable, you have a datum. a datum. That is a singular form of a variable. That you have a datum. Many datum or collection of datum is what we call data. So data is plural, datum is singular. And because it's just a measurement of variables, the type of data will also follow the type of variables. So we have quantitative data, we have qualitative data. And under the quantitative data, it also follows the variation, the options we have. That's for variables, we have the continuous data, we have discrete data. Qualitative data, we have nominal data, ordinal data. So it's just the same thing with variables. It's just that these are measured variables. And last week, we started with the analysis strategy. And this is where we spend most of our time, univariate variable, because that is where you have more of descriptive statistics. You know, these two are actually inferential. They are inferential statistics to a large extent, and that is where we'll be starting today. And for the descriptive statistics, this was what we did invariably last week. You know, I told us that the kind of analysis that you will do is dependent on the type of variable. And you can see that for continuous variable, we saw last week the measures of central tendency, mean, median, mode, variation, we saw variance, standard deviation range, percentile, interquartile range, and distribution, when we spoke about the normal distribution of a continuous variable. That's the normal curve. That was where we emphasized more. And for the plots, we looked at histogram, we saw box plot, stem plot, dot plot, line chart, time series plot. All these are for continuous variable under quantitative. And then we looked at the other side, which is the qualitative variable, and that's the categorical type, where we can have frequencies. That's the frequency table, the count, the tallies, the cumulative frequency, the relative frequency, percentages. We did not do odds last week. It's something we are going to come across as we continue. And for the plots that we have for categorical variables, we saw a bar chart, a pie chart, and I remember we spoke about a Pareto graph. So this was just, this is just like a summary of what we did last week. So for statistics, we have descriptive statistics, which was done last week. And then we are starting the concept of inferential statistics, which is what we are going to be talking about today and for the next two lectures ahead. So inferential statistics allows researchers to make decisions or inferences by interpreting data patterns. They make decisions or inferences by interpreting data patterns. So looking at this chart, inferential statistics can be divided into two: estimation or hypothesis testing. When we say estimations, there are other sub-classifications like point estimates, and then we have interval estimate. By the way, an example of point estimate is mean. That's sample mean. And if you remember, when we were talking about mean last week, I said it's very crucial and very useful in inferential statistics. So mean is an example of point estimate that we use in inferential statistics. We also have sample proportion. Sample proportion is also an example. And then we have least square. Least square method is one of the analysis that we do in regression. And then we have maximum likelihood. All these are just examples of point estimates. For the interval estimate, a very good example that all of us might be aware or familiar with is the confidence interval. So it's an estimate that helps us to delineate a particular range where a kind of value can be found. That's the interval estimate. We have confidence interval, and then maybe you have not heard of this. There's another interval we have. We call it credible interval. This is another type of interval that is used to estimate parameters. And when we talk of parameters, we are referring to population. I don't know if I've mentioned it before, maybe not in this class. You know, when you have a population of so many units, and then you select a bit out of the population, and you have maybe 3 or 4, all the attributes of the population is called parameters. While the attributes of your sample is what we call statistics. So if I'm mentioning parameters, I want you to know the difference. The attributes of your population is called parameter. The attributes of your sample is called statistics. So the other type of inferential statistic is the hypothesis testing. And this can be parametric tests or non-parametric tests. And I'm going to explain that briefly, for us to have an idea before we continue. When we say hypothesis testing, it's a method used to determine if there is enough evidence in a sample, that's in a sample data, to draw conclusions about the population. So you are using the sample to make inferences about what might be happening in the population. And there are so many types of hypothesis testing, like t-test, chi-square, ANOVA, regression, and all these non-parametric tests. There are plenty of them. Now, the particular type of test you are going to use will depend, number one, on the type of question that you have, the type of data you have collected, the distribution, that's if it's normally distributed or not, the sample size, and many other factors. So when your distribution, if it is normally distributed or not normally distributed, is when we now talk about the issue of parametric or non-parametric. And I was following the discussion on the platform, and there was this robust discussion about normality, parametric tests, and non-parametric tests. And I'm so excited about that. Sincerely, very excited. It shows that we are following. So depending on the type of data distribution you have, that is when you can now choose to do a parametric test or a non-parametric test. So the key difference between parametric and non-parametric is that the parametric relies on statistical distributions. And what that means is that you have an assumption that the source of your data from the population follows a normal distribution. Please listen to that statement again. That parametric test relies on the statistical distribution, and that's an assumption that the source of your data, that is where you sourced your data from the population. That assumption says that it follows a normal distribution, whereas the non-parametric does not depend on any distribution. So parametric test makes assumptions about the parameters. So you can see the word parametric, parameters. So it makes assumption about the parameters. That is the defining properties from the population, from where your data were drawn. And in contrast, non-parametric does not make such assumptions. And by default, non-parametric are most commonly used for variables at nominal or ordinal. Most commonly used for variables at nominal or ordinal. It doesn't mean that we don't use them for other kind of continuous variables. So when you have a continuous variable, I think the first thing you should do is to test for normality. And I saw that we have a lengthy list of people talking about normality tests. Where is it? On the platform, that was on the WhatsApp platform. I just want to give us some ways, maybe I should just mention them, some ways via which you can test for normality in your data before you choose the particular kind of test you are going to do. Number one, you can use histogram. If you remember, we spoke about histogram, that when you have a bell-shaped design or appearance of your histogram, it gives you a sign that it is normally distributed. And we spoke about skewness. Skewness is also a method of checking, for normality. And likewise, kurtosis will also be a method. If skewness is a method, kurtosis will also be a method to check for normality. Then mean. I remember Prof even mentioned that when you have your mean, your median, and mode being similar, is a sign that your data is actually normal. And I mentioned that last week when we were talking about the central tendency. There's something we call a PP plot. Is also a method to check for normality. And there's another one we call a QQ plot. All these are methods to check for normality. And then we have the ones I saw on the platform, that's number 7. We have the Kolmogorov-Smirnov test, and then we have the Shapiro-Wilk. We have the Shapiro-Wilk test. They're all tests of normality. And lastly, I can add that we have box plots. Box plot can also check for normality. So we have about 9 different ways you can check for normality before you choose the particular type of analysis you are going to do. I go over it again. We have histogram, we have skewness, kurtosis, we have mean, that is measures of central tendency. We have PP plot, QQ plot, we have Kolmogorov-Smirnov test, we have Shapiro-Wilk test, and then we have box plots. So like I was explaining earlier on, this is a population. From your population you sampled to have a sample. So whenever we are doing descriptive statistics is always done on a sample. Now, when you are analyzing your sample to make inferences on your population, that is where inferential statistics comes in. As simple as that. This picture just explains all I've been trying to say ab initio. So from your population, you sample to have a sample. You do your sampling, rather, to have a sample. On your sample, you can describe your sample. But if you want to analyze your sample to make inferences, to tell us what might be happening in the population at large, we call that process inferential statistics. And that can be either by estimation or by hypothesis testing. Under hypothesis testing, it can be either a parametric test or a non-parametric test. If it's under estimation, it can be either by point estimation or interval estimation. So these two are inferential statistics, and we'll be looking at the bivariate type, which involve the measurement or checking relationship, association, correlation, whatever it is, between two variables. So this is an example of two variables, and different kinds of analysis that might come up using two variables. Remember what we spoke about types of variable. It still comes handy here. So when we have two variables, where the two variables, that is the independent variable and the dependent variable, are both categorical, either nominal or they are ordinal. That was why we spent a lot of time trying to look at types of variables, because if you don't understand the basic foundation of variables, it will be difficult to apply a quantitative data analysis. So if we have two variables that you are comparing or checking their relationship or association or correlation or whatever, and both variables are categorical, that means your X is categorical, your Y is categorical, definitely by default, if you follow our definition of parametric and non-parametric, the analysis you are going to use are non-parametric, because non-parametric are cardinally used for nominal and ordinal variables. And all these are non-parametric tests, chi-square, Fisher's exact, McNeema, Munster-Hessel, all these are non-parametrics. So when the variables have two categories, remember we spoke about the issue of binary or dichotomous, then we use chi-square or Fisher's exact or McNeema. But when either of the two is more than two categories, chi-square is still useful, is still indicated, and then we have Munster-Hessel test. Now, on the other side, if one of the variable, that's your dependent variable, is continuous, and then your independent variable is categorical, that is where all those terminologies become very handy. When your dependent variable is continuous and your independent variable is categorical. Let me just quickly give an example. So maybe this is class A. The people on the platform now are class A. And then I have another class B. That is, and I want to look at the effects, or not just the effects, maybe the knowledge of research methodology among class A and compare it to the knowledge of research methodology among class B. So the classes are my independent variable now. The knowledge is my dependent variable, my Y. Classes is my X. So classes now is categorical. Classes is categorical. And my dependent variable knowledge is continuous. It's something I can measure, something I can calculate and have a measurement. For that particular type, we can have all these varieties. Now, even for this variety, we might need to check if my knowledge fulfills being a parametric, fulfills a normal distribution or not. So if my Y, my knowledge, is normally distributed, then I can use a t-test. If my Y is not normally distributed, then I have other options like Wilcoxon and Wilcoxon sign. We'll talk about that in our next class. Now, if my Y is normal, it follows a normal distribution. However, my classes are more than 2. I can't use a t-test again and now start talking about ANOVA. But if my Y is not normal, that means it doesn't follow a normal distribution, and I still have more than 2 classes, it's no longer binary, then I'll be talking about a Kruskal-Wallis test. Now, the other option is when both my X and my Y are both continuous. Both of them are continuous. That's where we'll be talking about scatter plots, simple linear regression, Pearson's correlation. But they might be continuous and they might not be normally distributed. That is where we start talking about Spearman's correlation, Kendall style B, Kendall style C. There are different methods of doing that, checking for their own relationship. So this is just a table to just talk about bivariate analysis, and that's like the beginning part of inferential statistics. Okay, all right, I'm seeing some marks all over the screen. Maybe somebody is touching their own screen somewhere. So today we are talking about correlation, to understand and interpret correlation, and then as time permits, we also look at chi-square, and most likely try and look at our SPSS to see if we can do some sample examples using SPSS. So we are starting with correlation, and we define correlation. It's a statistical tool that helps us to measure, that's number one, describe, number two, and then analyze the degree of relationship between two variables. Correlation helps us to measure, describe, and analyze, the degree of relationship between two variables. So it deals with the association between two or more variables. That's correlation. So when we talk about a straight line, I remember we spoke about the equation of a straight line, maybe when we're in the university or in secondary school. There are three things you can measure in a straight line. Number one is to measure the gradient, which we call the dy dx. I remember that term sounds a bit familiar. The gradient is a measure of how the line slopes, something like that. We want to know the changes in the ascension and in the other label line. That's for one thing you can measure in a straight line. You can also measure the intercept. That is where the line cuts or hits the y-axis. That is the intercept. But the one that concerns us today is the correlation of how well the line fits the data, which is called correlation. How well, a measure of how well the line interprets the data. That's another word for fits the data. How well it interprets the data. So we said that there's a relationship when changes in one variable tends to be accompanied by consistent and predictable changes in the other variable. So there's a relationship. So it's like this. We can have a variable that is increasing and the other variable too is increasing with it. That's consistent and predictable. We can have a variable that is reducing and the other variable is also reducing with it. That this is A, this is B. We can have a variable that is increasing and the other one is decreasing, that is C. And then we can have a variable that is decreasing and the other one is increasing, that is D. So these are different situations where a relationship can exist. So if two variables vary in such a way that movement in one is accompanied by movement in the other, they are called, a cause and effect relationship. By the way, these two is what we call a positive correlation. This two is what we call a negative correlation. And I'm going to talk about them as we continue. Causation always implies correlation, but correlation does not necessarily imply causation. Let me go over it again. You might find relationship between two variables such that as one is increasing, the other one is increasing. We call that one causation. We call it correlation. So it doesn't mean that because one is improving, the other one is improving. It doesn't mean that one of them is the one causing the other one. My statistics professor gave us a good example many years ago that they did a study, where they were measuring how short a miniskirt is. A miniskirt, and they were comparing it to IQ of the students. And they found out that the shorter the miniskirt, the more intelligent the students. So the question is, does it mean that if you have a short skirt, does it mean that you're intelligent? No, that was just a correlation. By chance, they just found that correlation. But it doesn't mean that you have to make your skirt very short to be intelligent. Eventually, people will be walking naked. So that's all I'm trying to say, that causation always implies correlation. But correlation does not mean that there's causation. And the degree of relationship between the variables under consideration is measured through correlation analysis. And analysis enables us to have an idea about the degree and direction of that relationship of the variables that we are studying. A correlation typically evaluates three aspects of the relationship: the direction, the type of correlation, that is the form, and the degree, that is the magnitude of correlation. And we are going to look at the three of them very fast. We start with the direction. So we can have a positive correlation or we can have a negative correlation. The direction of the relationship is measured by the sign plus or minus. It can be positive or negative. Like I said in like 2 slides behind, a positive correlation means that the 2 variables tend to change in the same direction. Remember I said one is increasing, the other is increasing. One is reducing, the other is reducing. These 2 are what we call a positive correlation. On the other side, a negative correlation means that they tend to change in opposite direction. So as one is increasing, the other is reducing. As the other one is reducing, the other is increasing. So these 2 are negative correlation. As simple as that. Please don't let it confuse you. So like I said, variables for positive relationship, they change in the same direction and they are indicated by the plus sign. The negative relationship, variables change in opposite direction, indicated by the negative sign. Look at the example here. As your height increases, so does your weight. The negative relationship, the more time you spend watching TV, the lower your exam grades. So there's just like an opposite direction. Now, the negative correlation is also called inverse correlation. In case you are seeing that word, that is what it means, inverse correlation. Why the positive is called direct correlation, in case you are seeing that term, so that you don't get confused. That's just a synonym to what we are talking about. So this is positive correlation. This is going up, this is going up. Likewise, if this is coming down and this is coming down, it's still positive. Negative correlation, one goes up, the other one comes down. One comes down, the other one goes up. As simple as that. Positive correlation, negative correlation. So it will help you in interpreting your results when you have done your study. So for the positive correlation, if the points cluster around a line that runs from lower left to upper right, so anytime you see positive correlation, it normally goes from lower left to upper right. That is a positive correlation. And this is an example of what we call a scatter plot. We are going to look more into it as we continue. On the other side, negative, okay, so you can see what I was talking about. Negative or inverse, positive or direct. Negative or inverse relationship is the point they tend to cluster around a line that runs from the upper left, and then they go down to lower right. So negative always starts from the upper left and then it turns down. When you have your scatter plot and you see the arrangement of your points coming from up down, that one is negative. The one that is from down up, that one is positive. That is talking about direction. Remember, direction can be positive or direction can be negative. Now let's talk about a form of correlation. The most common form is a linear relationship. That's a straight line. And that is the one we measure using Pearson correlation. There can also be other types of form, like we call them curvilinear or non-linear. But the most common form, which concerns us in this class, is the linear relationship. The linear correlation is said to be linear when the amount of change in one variable tends to bear a constant ratio to the amount of change in the other variable. That is when we say it's linear, a constant ratio. The graph of that variable will have a straight line. When you plot it on the chart, you have a straight line. Look at this example, x from 1 to 8, and then 5 from y from 5 to 19. If you look at x, as x is increasing by every 1, 1, 1, y is increasing by every 2, 2, 2. So we have a constant ratio of increase in the other dependent variable. The non-linear does not bear a constant ratio, so it can vary. And when we talk of non-linear, there are things like quadratic equation, exponential relationships. All those ones are non-linear. But the linear relationship or correlation is the one that actually concerns us. So this one is a perfect example of a positive linear relationship or correlation. Remember, positive from lower left to upper right. Positive. And it's a perfect example because it's a straight line. And these are examples of linear relationships and curvilinear. You can see that the line that is interpreting this relationship is not straight, it's bent. All these are curvilinear or non-linear. But if you can have a straight line, either positive or negative, we call that a linear relationship. So this is the form of relationship. All these ones are non-linear, just different examples of different kind of variables with themselves. And then the third type is the degree, that's the magnitude. So we say that there's a relationship between X and Y. How strong, how big is that relationship? What's the magnitude? That is the third one when we talk about the degree. A measure of correlation is called the correlation coefficient, R. The degree or the strength of consistency of the relationship is measured by the numerical value of the correlation. When we have a value of 1, that indicates perfect relationship, and that's 100%. That means that X predicts Y perfectly. And when there's a value of 0, that means that there is no correlation or no relationship. So our degree of relationship can actually be between 1, that's -1, going all to +1. That is the range of our relationship. So we can have a perfect negative and we can have a perfect positive. You can't have anything beyond that. You can't predict beyond 100%, or you cannot correlate. A relationship cannot be more than 100%. So it's either a perfect negative or a perfect positive. This one is an example of a positive correlation. Now, the correlation actually, looking at the ... that we have there, this line is what we call the line of best fit, and it's always inserted by the computer. You can insert it by the computer. It's not something you draw arbitrarily, And then we have that correlation, but you can see that if you put like a circle around all the dots, it's a bit like compacted together. And you can see it is positive because it's starting from lower left and going up to upper right. It's a positive relationship and it's strong. The positive sign shows that it is from lower left to upper right. And we have 0.80, that is 80%. So weight and height are related by 80%. So we can say that height determines 80% of the weight. Height of a person determines 80% of the weight. There are other factors that can determine the weight, but height has a value of about 80%, in explaining the weight of an individual. That's positive, and it is strong. That is why we have 0.8. This one, you can see that if you are to put a circle around everything, it's becoming a bit wider. Unlike the previous slide, this one is moderate positive, and you can see it's 0.4. That's like 40%. The positive sign there is what is telling us the direction. Now, you can see this one is perfect negative. They all fall on a straight line. That is 100%. That's why we're having -1.0 here. Negative being the minus, 1 being the 100%. Perfect negative. Then we have here maybe moderate negative. You can see that the line comes from upper left to lower right. That's moderate negative. I won't say this is moderate negative. It's actually strong negative, because we are having about 80%. Something moderate should be like maybe 60 and 50%, but that is how you identify the degree. We have weak negative here, and that is -0.2. We have no correlation here, because if I'm to draw a circle around this, it looks like a perfect circle. So there's no correlation, and that's why it's 0. There's no correlation between your IQ and your height. Your knowledge is not based on how tall you are, or your intelligence rather, is not based on how tall you are. So there's no correlation in that regard. These are just examples for us to look at. In A, we have a perfect negative. In B, we have no correlation. In C, we have, I can say moderate positive. I can say moderate positive. In D, I can say very weak negative. Very weak negative. You can see that though it's a bit circular, but it's still tilting to the left. Okay? And these are other examples, to show you the degree of correlation. You can see that this line is compacted together. The circle is a bit like compressed. That's why it's stronger than the others. And then it starts from positive, strong positive, that is plus 0.8. We now have plus 0.6. We have plus 0.4. We have plus 0.2. All these are positive. All these are positive, but they are in different level of strength or degree of positive. I think it's Riskat Toyosi. You are putting lines all over the screen. Riskat Toyosi, please just stop that. It's affecting the appearance of the screen. Thank you. This is an example to show us what we mean by a scatter plot. And we are still going to talk about that as we continue. We have about 14 students here. That is A to N, 14 students. And we have the family income of the parents and the average grade of the students. The family income is in thousands of dollars. Both of them, so this is X, this is Y. A sample question will have been, is there a correlation between the income of the parents and the grade of the students? So we have X and Y, and if you look at the two of them, they are both continuous variables. They are both continuous variables. So it's subject, and we can use, what's it called? We can use a scatter plot to assess it. So we have here the chart done. And if you look at it, I'll just try and put a circle around the dot. From the way it looks, it's positive, but we don't know how strong the degree of correlation between the two. But definitely it shows that there's some kind of relationship, and that relationship is tending towards positive. And when we do our correlation coefficient, it comes in different values. Like I told us, it can be from -1 to +1. And so we can have all manners of values between -1 to +1. And if we have 0, like I showed us earlier on, it means there's no correlation. Anything from 0 to 0.2, either positive or negative, it means very weak correlation. Likewise, from 2 to 0.4, 0.2 to 0.4, weak correlation, 0.4 to 0.6, moderately strong, 0.6 to 0.8, strong correlation, 0.8 to 1, very strong correlation. When you have 1, that is perfect correlation, perfect 1. That is perfect correlation. So like I said, it can be from 0 to 1, either positive or negative. Types of correlation is, we have two types. The simple correlation, when you are just considering two variables, or multiple correlations, when you have more than two variables, 3 or more, So, but we are going to be looking more or spending more time on the simple correlation. Now, let's look at an example of how correlation is done. Normally, if you have done or you have a research question, it's your question that will determine if you need to do a correlation. And that question will be amenable to an hypothesis. So you are testing your hypothesis for correlation. Number one is to generate your null hypothesis, which I'm sure we are familiar with, which says that there's no correlation between A and B. No, so let me use the income in the previous slide, the income and the grade. So we can say there's no correlation between the income of the parents and the grades of the students. There's no correlation between the income of the parents and the grade of the student. And the alternative, we now say there is a correlation between the income of the parents and the grades of the student. And this can be positive or negative. And that's why it's an alternative, a two-tailed alternative for hypothesis. And the next step is for us to calculate our R value, which is our correlation coefficient. And then we check our P value to see if our finding is either positive or, if it's significant or not significant. So for example, if we got a -0.4 as our R value and our P value is 0.007, this is significant. And that means that we are going to knock off the null hypothesis and go with the alternative hypothesis. The interpretations shows that there's an inverse or negative. Remember I said that's the synonym. There's an inverse or negative correlation between the income of the parents and the grade of the student. So what does that mean? The more the parents' income, the lower the grade of the student. And that is the interpretation of your finding. The more the income of the parents, the lower the grade. That is why it is inverse or negative. If it was positive, it would have been on the same direction. Either they are increasing at the same time or they are decreasing at the same time. And vice versa. Okay? How do we study correlation? Number one is scattered plots. Number two is Pearson. Number three, ma'am.
Please, can you clean those? Is it possible that you clean those? It's affecting vision.
Yeah, let me see if I can erase. It's not going. It's the person that puts it there that will be able to remove it. I think it's Riskat. I saw a name, Riskat something. The person will be able to on her.
Yes, I was trying to chat about it. Seems she has gone off.
Yeah, the person will just like erase all ink.
Yeah, the alternative is to stop sharing and reshare.
And start afresh, yeah?
Reshare it, yes.
Yes, sir.
Okay,
it's affecting vision badly.
Yes, it's even affecting me here too. Okay. So let me just do that.
Thank you, sir.
All right. One minute, please.
Just to add, For those of us joining with our phone, I mean, with our phones, this error can occur if you are pressing on your screen. So please just avoid writing on your screen while following the class.
Is this better?
It's up. Thanks.
Yes, sir.
Yes, it is.
It's okay, sir.
Beautiful. So like I said, the methods of studying correlation, we have the scatter plot or scatter diagram, we have the Pearson's correlation and the Spearman's correlation. So let's quickly go through them, starting with the scatter diagram method. So this is just a graphical method of checking the relationship between two variables. You know, where we have our X and Y, the two variables either dependent and independent, and especially if both of them are continuous variables. So it portrays the relationship of the variables graphically. And I have two examples here. I have on this side, this is A, and this is B. On the A side, I have SPB, which I can just, they're all like hypothetical figures, maybe systolic blood pressure, so to say, and then the age of children. And then on the other side, I have the weight and the age of children. And for the first one, that is A, looking at the scatter plot, it's been charted here, you know. From the way it even looks, based on what we've been discussing, this is obviously positive, starting from the lower left and going to upper right. And then if I want to like get a circle around it, you could see that it's compacted. So it's a strong relationship and positive, okay? On the other side, look at this scatter plot between the weight and age of children. You will see that it's even disjointed. We are with an observation at that side. This is a good example of identifying outliers because this is corresponding to age. This is more than 100 age. And so if we go back to our variables, you will notice that there's an error somewhere here, the one corresponding to 52. Instead of 11.6, it was pressed like twice, or 3 times, so you now have 111.6. So if we correct that particular error and we plot again, we corrected it here, and we plot again, you can see the scatter plot. Now, this is one deficiency with scatter plot because sometimes the graphs come up like this and you can't actually say if it is positive or negative. But this is a scatter plot and you can see it looks like a bloated circle. We can't say it's positive or negative, but we need a scatter plot as the initial step when calculating correlation. So scatter plot comes like this. This one now, I can put a line and say this is a positive relationship. This one too is positive, but moderately positive, perfect negative. You know, they're all like on a straight line. This one is also negative, moderate negative correlation. This one is weak negative. It's still like tending towards this direction, weak negative. All these are examples of scatter plot. This one looks like a good circle, you know, so we can say there's no correlation. We are the ones that are just saying no correlation. By the time we put in a line of best fit, the computer might tell us that no, there's still a mild correlation, either positive or negative. So the advantages of scatter plot is that it is non-mathematical, it's very fast, it's straightforward, and it's usually the first step when you are trying to check for correlation, okay? The disadvantage is that you cannot have the degree. So we can just say it is positive or negative, but what is the degree in value? You can't get that from scatter plot except to go further. The next method is the Pearson's correlation, okay? And this one, we compute it when we have the scores for our independent variable and dependent variable for each individual in the sample. The Pearson correlation requires that the scores be numerical, they are continuous. So we use it with interval or ratio scale. You can see where all those terminologies comes handy. There are other methods when they are not, the scale of measurement is not interval or ratio. Like if it is ordinal, there are other methods, and that is Spearman's. We will get there. The Pearson correlation measures the direction and the degree between the two variables. So once you do that R calculation, it gives you the two values, the direction and degree, and it's the most common correlation coefficient that we work with, and it's expressed by the value of R, which is between -1 down to +1, like I said earlier on, from -1 down to +1. So you can have a perfect negative down to perfect positive. To compute the Pearson's correlation, there are two methods we can work with manually, which we just rushed through, and then we have the calculation using softwares. You need to first measure the variability of the initial scores. That's for the dependent variables and the independent variables. And then you compute the sum of square. Remember, I said keep that terminology handy. When we were talking about variance in our last class, I said just keep it handy. Sum of squares, which is normally, the mean minus the variable, and then you square it, and you do it for all the variables. This is x1, x2, x3, and xn. You add everything. That is the sum of squares. Then you check for the covariability, the tendency of x and y to vary together, and you multiply that, which we call the sum of products. We'll see an example now. And then the formula is found by computing the ratio. So our R is actually SP, that's the sum of products. I'm just expanding that formula. Sum of square for x times sum of square for y. That is that formula. Once we have a value for that, we have our R, and our R can be positive or negative or zero, and that will give us the degree and the direction of our correlation. So this is how the table will look like if we are going to use this method. We have our x, we have our y, then we have our mean minus x, mean of x minus individual x, mean of y minus individual y. We square the sum of square, the variation here, we square the variation here, and this is the sum of products. And then we add everything and we have our value. So let's just have an example. Here we have 6 people and we have their ages, 43, 21, 25, 42, 57, 59. And their glucose level, 99, 65, down to 81. So these are our X and our Y. And the question is like, does age affect the glucose level? Is there a relationship between age and glucose level? Is there a correlation between age and glucose level? I've given 3 variants of how the question can be asked. So using this method manually, we can calculate the sum of our age divided by 6, and that gives us our mean. Likewise, the sum of the glucose level divided by 6, it gives us our mean for y. And then we can go to the next step of subtracting the individual variables. So mean 41.2 minus 43, it gives us minus 1.8. 41.2 minus 21 gives us 20.2 down to the last value. And that's how we got this column. The same thing with our glucose level. The mean is 81. 81 minus 99 gives us minus 18. 81 minus 65 gives us 16. Down to this value, 81 minus 81, that's how we got 0. That's the next step. And then we can now go to the next slide where we have this particular value here. We square it. So minus 1.8 squared, 3.24, 20.2 squared, 408.04, down to the last value. Likewise, here too, minus 18, squared, 324, 16 squared, 256, and down to the last value, 0 squared is 0. That's how we got that place. And for the third, for the next slide, where we have the product of x and y, is just multiplying this by this. And that's what we have here. Minus 1.8 times minus 18, 32.4. 20.2 times 16, 323.2, down to the last value, 0 times minus 17.8 is 0. So the next slide is now to add. Remember, is the sum. So the next slide is just the addition of those values. And for the sum of square for x, we have 1260.84. Sum of square for y, we have 656. Sum of square of the product, we have 478. And then we can now put those figures in the formula. You remember I said the formula is the sum of square divided by the sum of products rather, divided by the sum of square of x, sum of square of y. Our R equals to that. If you insert the figures, so this is going to be 478 divided by, this is 1260.84 times 656. By the time you calculate this out, you will get 0.52 as our R value. Now, we are not having any positive sign in front, but by default, it is positive since there's no negative. So there is like a moderately strong relationship between age and glucose level. And the level of correlation coefficient is 0.5. That is for that, as simple as that. That's the first method, of calculating correlation coefficient. That's the Pearson correlation coefficient. The other method is another formula, and that is the formula there. It has to do with having your values between X and Y. You know, you have the summation of X, the summation of Y, where your N is the number of pairs. In the previous slide, our N there were 6 people or 6 patients, you know, and then we can find out the values of all these these figures here and substitute in the formula. So look at this example here. We calculate the sum of the 2 series, the sum of the X, the sum of the Y. We calculate the square of each value of X and Y, and we find the sum. We also find the corresponding value, that is X times Y, and then we find the product of, or the sum of the product of X, Y, and we substitute in the formula. And I'm going to use the same values we used in the previous example, where we have the age, and then we also have the glucose level. And there are 6 subjects. So this is our N. And then the next thing for us to do is to find the product of X and Y. You know, the product of X and Y for each of the 6 individuals. That is 43 times 99, 21 times 65, on and on down there. And once we do that, we have those figures. The next one is to find the square. This one, that's to find the square of each of the figures there. 43 squared, 21 squared, 25 squared, and that will be populated here. And that is what we have there. And the next one is to find the square of all our Y individually, and then it will be populated here. And that's what we have there. And then we can now find the sum. We need to find the sum of each of these values. That is the summation, this summation, that. And we have that there. Now that we have all these values, we just substitute them into the formula, and that's the formula, and those are the values. And once we substitute them and we do our calculation, we see end up with 0.52. Remember, we had 0.52 using the first method. So basically, the 2 of them give us, roughly the same answer. So that is how we can calculate our Pearson correlation manually. But as it is, we are not doing that manually. It's just for you to understand the basics behind it. We do it using our softwares now. So I've discussed this about the degree of correlation. If it goes towards -1, it's negative. It goes towards +1, it's positive. This is perfect positive. This is perfect negative. It's just an interpretation of the coefficient. When we do a correlation analysis using SPSS, we have an output that looks like this. So what we are going to quickly do is to look at how to interpret this output in case you have an output from your statistician. Look at this cell A. If you look at cell A, it is height against height. So you are not going to have any value there because it's a constant. Height against height. You won't get anything. Look at cell D. It is also weight against weight. So you are going to have like an empty space between the 2. Now let's go back to cell A. In cell A, we have our N as 408. In cell D, we have our N as 376. You can see that there is disparity. So what we have in cell B is 354. That means that out of the height and the weight values, there were 354 that were pairs, that you could see their height value and their weight value. That is why we can correlate them together. We have values for height, 408. We have values for weight, 376. But when we were talking of correlation, we have 354. That shows that out of this 408 and 376, only 354 had both values for height and weight. And that is where we can have the correlation. And what you have in B is what you have in C, because correlating height and weight, we give you the same value as correlating weight and height. So B and D is just a mirror image of each other. Now, our Pearson correlation in B is 0.513. Our P value is 0.000, and our N is 354. So our value there shows that it is moderately strong and positive. Moderately positive, correlation 0.5. There's no negative there. That is how you interpret your correlation table. There are situations where you can have multiple values correlating them with themselves. Here, that is on this, let's say this is our chart B. I have variable 1, 2, 3, 4, 5 on the top, and on the left, variable 1, 2, 3, 4, 5. The variables can be anything. For example, I just say 1 can be age, 2 can be income, 3 can be weight, 4 can be height, 5 can be exam score. So for variable 1, if I'm correlating 1 with 1, that is why you have this empty space here. And it continues like that and runs down because variable 2 compared with variable 2 will give you nothing. On and on and on and on like that. So let me just use an example of variable 1 and variable 4, and let's look at what we have. So this is variable 1. Variable 1 I said is age. Variable 4 I said is height. So correlating age with height, this is the value we have here. You can say that it's minus 0.15. That is negative. Our p-value is 0.02, is significant, and we have a total number of 214 pairs of variables or values. So that one is a weak negative. From the way we have seen it, minus is negative, and 0.12, if you remember the interpretation, 0 to 0.2 is weak. So that's a weak negative. You put your p-value and you put the number of pairs or values that's available. And that is how you will check them one by one. And if I go also, that is variable 1 and 4. Now let me do 4 and 1. 4 and 1. You can see it here. It's the same thing with what we have here. Like I told you, it's just the same. If you correlate 1 and 4 and 4 and 1, you will get the same value. So whichever one you choose to report will give you the same value, and on and on and on for all the other variables. What are the assumptions in Pearson's correlation? We assume that there's a linear relationship. Remember the equation of the straight line. We assume there's a linear relationship between the two variables. That means when the two variables are plotted on a scatter plot, a straight line will be formed by the point. There's also an assumption that there's the cause and effect relationship between the variables. So these are just assumptions that we have for correlation, Pearson correlation. The advantage of Pearson correlation is that in one value you have the direction and you have the degree. Direction by positive or negative, degree by the values of the R. And that is why it is the most common correlation analysis that we work with. The limitation is that there's always this assumption that there's a straight line. Sometimes it might not be straight, it might be curvilinear. And another problem is that the value of R is difficult to interpret. Although it gives us the degree, but that is not the interpretation. So the value of correlation coefficient is affected by extreme values. That's another limitation. And it can be time consuming if we were to do it manually. But good, I said that we have softwares that gets done in less than a second or so. Okay? So that brings us to the concept of coefficient of determination. And please, I require our rapt attention for this particular explanation. The convenient way of interpreting the value of our correlation coefficient is to use the square of that coefficient. And we call that square the coefficient of determination, or R squared. R squared. I want us to get the understanding here because we will meet it in front. I think when we start talking about regression, you will come across it again in regression. And it's very important we grasp it here so that by then it will be easier. So suppose we have done our Pearson correlation and we get a value of R as 0.9, that is positive 0.9. And if you are to go by the interpretation of R, this is very strong. You know, it's close to 1. Our R squared is 0.81. This will mean that 81% of the variation in our dependent variable is explained by our independent variable. And I have some examples here which I will use to explain what I'm talking about. So for example, the correlation between height and weight was 0.90. And then we square it for our coefficient of determination, and it gives us 0.81 as our square. If we multiply this by 100%, this gives us 81%. So how do we interpret that? This means that 81% of the weight of an individual is determined by the height of the individual. That is how coefficient of determination comes in. This means that 81% of the weight of an individual is determined by the height. That means there are about 19 other percent determined either by the diet, determined by the clothing, by other factors. But if you have the height of the individual, we can determine the 81% of the weight of the individual. Now, I want you to also understand that I have to arrange it in a logical way. Look at the second example, exercise and blood pressure. By logic, the more exercise you do, the less your blood pressure, by logic. So invariably, if we have our R as 0.9, it's supposed to be minus 0.9, because the more exercise you do, the less your BP should be. Now, when we now square it as our coefficient of determination, and that gives us 81% because the negative sign will disappear, we can now interpret it that 81% of the reduction in blood pressure can be attributed to exercise. We need to be able to interpret our coefficient of determination. 81% of the blood pressure reduction can be attributed to exercise. And the other last example here, time spent reading and exam score, let's assume that our R squared is 81%. We can say that the score in our exam can be attributed, 81% of performance in exam can be attributed, to the time spent reading. So maybe the remaining 19% can be natural intelligence, it can be availability of textbooks, it can be school attendance, it can be note-taking, it can be discussion, blah, blah, blah. But if we have to look at all the variables that can determine exam success, from this particular correlation, 81% of it can be dependent or can be attributed to the time you spent reading. I hope it makes sense, because it's very important we understand how to explain coefficient of determination. So the maximum value of R squared is also 1, because the maximum number amount you can have is 100%, and the formula for the coefficient of determination is explained variation over total variation. Explained variation, especially by your independent variable, over total variation. So suppose we have our R as 0.6 and another value of our R as 0.3. It doesn't mean that the first one is twice as strong as the second. We understand the value of R when we square them as coefficient of determination. For example, when R is 0.6, the coefficient of determination is 0.36. And when R is 0.3, the R squared is 0.03. So it implies that in the first case, 36% of the total variation, or our Y, is explained. And in the second case, only 9% of the Y is explained. So please, this does not mean that it is twice the value. It is when you multiply it out, when you square them out, that you now have the interpretation. So how do we report our correlation? You report by putting your R, the degrees of freedom. The degrees of freedom, normally we have, that is the N minus 2, because there are two variables you are comparing. Then you put your R statistics, which is the Pearson correlation and the p-value. And your R statistics should be reported to at least a minimum of 2 decimal places. And the p-value should be reported to 3 decimal places. So invariably, if this was your SPSS output, you interpret it or you report it like there was a moderately positive. Why the word moderate? Because it's about 0.5. Positive correlation between height and weight. Our R is 352. This is our N minus 2. That's how we got the degrees of freedom. And our R value is actually 0.51. That 3 shouldn't be there, because we are advised to report it to 2 decimal places, but our p-value to 3 decimal places, and our p-value is 0.000. This is how you report your R, and by now, you should know how to explain that. If you want to now know how much of weight is explained by height, you have to now, what's it called? You do a coefficient of determination by squaring the value of your R, and then you can explain further. So these are some things to note. There are 2 ways to report p-value. The first way is to cite the alpha value. The second way, which is the preferred way, is to report the exact value. This first way is when people say that p less than so or p greater than so. But the second way is where you say p equals to so, you give us the exact value. The other thing to note is that if your p-value is less than 0.001, you can just say that p less than 0.001. Rather than give the exact value, because you might have to be talking about 4 decimal points but we are told that we should limit it to 3. And I said the R statistics should be to 2 decimal points, and you should always remember to remove the initial 0 before both the R value and the P value. So if we have 0.34, it is just 0.34 that you need to write, not 0.34, and likewise for the P value. You don't need to provide the formula for your R, and the degrees of freedom, like I said, is the number of data points or number of pairs minus 2. That's how you get your degree of freedom. And that's how we were able to get this narration here, for how to report our R. The last method of studying correlation, and I'm going to be a bit faster, is the Spearman's rank correlation coefficient. And this particular word here, I'm giving it out, rank correlation, to show that it is used for rank ordered variable or ordinal variables. So you can see why you must know your variables very well. If your variables, your X and your Y, if both of them are ordinal variables, you cannot use Pearson's correlation. You have to use Spearman's correlation. Otherwise, you have a wrong value and then you have a wrong result and a wrong interpretation and wrong everything. So please, very important, you have to know your type of value and the measurement scale. Once you are sure that your X is ordinal and your Y is ordinal, you use a Spearman's rank correlation coefficient. When statistical series in which the variables under study are not capable of quantitative measurements, but can be arranged in serial order, either ascending or descending, the Pearson's correlation cannot be used. But Spearman's rank correlation is what you should use. And this is the formula. This formula is the same with what we have here. Our R here is the rank correlation coefficient. For the previous one, we have the Pearson's correlation coefficient as a small r, but for this particular one, the rank Spearman is a big R. And this D is just the difference between the paired items in the series. And I will show us an example. So the rank in X minus the rank in Y, and then you find it, the square, and you sum the square divided by the number of pairs raised to power 3 minus the number of square. N is the total number of pairs. And our rank coefficient is denoted by the symbol rho. We'll just do a small example in the class and then we'll continue. So the Spearman correlation is used in 2 general situations between 2 ordinal variables, that is both X and Y consist of ranks, or in a situation where you convert your scores to ranks. You can have exam scores. Exam scores are continuous variable, but you can rank them by 1st, 2nd, 3rd, 4th, 5th down. So that's another situation where you can use the Spearman's correlations. Okay, and the calculation requires 2 variables are observed for each individual, and the observations for each variables are rank ordered. You will notice that the word rank is reoccurring. Please, very important. You use Spearman's for a rank ordered variable or ordinal variables. After the variables have been ranked, then you compute using the Spearman's correlation. But if you are working with original scores, you can use your Pearson formula. But if you are working with the ranked values of the scores, then you use the Spearman. Okay, this is an example. Microsoft shortlisted 10 candidates for a final selection interview, and they were examined in both written and oral communication skills. And they were ranked as follows. They were ranked. That is not their scores. So their scores have been converted to ranks. That's all I'm trying to emphasize. Their scores have been converted to ranks. So this candidate number 7 apparently is the best. It was number 1. It was first in both written and first in the oral communication. So those are their different ranks for 10 different candidates. The question is, find whether there's a correlation between the written and oral communication skills of the shortlisted candidates, and that's our formula. And we are going to quickly do maybe a classwork here. So the first thing we have to find out here is the value of D. And we said D is the rank in X minus rank in Y. So here it is -2, here it is 0, 0, here it is 4, that's 10 minus 6. Here is also -2, here it is 1, 0, 0, -2, 1. As simple as that. Then we have to do our D square. This is going to be 4, 0, 0, 16, 4, 1, 0, 0, 4, 1. And the next thing is to sum everything up. That's 4 plus 16, that's 20, 24, 25, another 5, that's 30. So our summation, what's it called? Summation D squared is 30. So let me, so we now have our P, our row, not P, equals to 1 minus, let me first calculate this first, 6 times 30, and we have 10 of them, that is 10 times 10 times 10, that is 1,000 minus 10. So this one gives us 180 over, I think 990. This cancels here. Let me just quickly do a small calculation using my phone because I want us to understand how this thing is done. That is 18 divided by 99, and that gives me 0.18. So this gives me 0.18. Now, 1 minus 0.18, I think that gives me 0.82. That is the value of my R, and that makes, and it's positive, although the mark is not there. And that shows that there's a strong correlation between their oral test and their written test. So, okay, from the class one, you can see that 0.82, the value of rank correlation is the same thing with that of the Pearson coefficient from -1 to +1. So, and it goes up and down. You know, if it is +1, perfect positive correlation, -1, perfect negative correlation, 0, no correlation, and then the values in between. This you can do at your convenience now that you have seen the example in the previous slide. But remember to first convert this to ranks. So you have to rank all these scores, you know, the performance in test and the time spent in study, rank it, and then see if you come out with a value that you can work with. The limitation is that it cannot be used for finding out correlation in grouped frequency. And when your N is more than 30, it is not indicated. Awesome. Can we quickly go to chi-square now, having spoken about correlation? Now, I'm bringing back this table or this chart talking about the inferential statistics. What we have done in the previous class and in the previous slides is the Spearman's correlation. We have done the scatter plot and we have done the Pearson's correlation. Remember, both are for continuous variables. Now we are coming to this side. We have both a categorical variable where we'll be talking about Pearson's chi-square. Pearson's chi-square. You know, there's Pearson's correlation, Pearson's chi-square. So it's trying to be confusing. Now, the objective of the chi-square is of this particular class to identify situations for where chi-square is appropriate, to calculate the chi-square and determine the significance of the test, and how to interpret the chi-square, and to relate our results to the null hypothesis, which is cardinal. So when do we use chi-square? In research questions that are like this, is there are the observed results different from the expected ones? You will see a situation like that. Does a relationship exist between maybe gender and color of skin? Both of them are categorical variables. That's an example. Does group A have a different outcome from group B? Is there an association between group A and group B? Where these ones are categorical. That's why it is going to be a non-parametric analysis, and it's going to be a chi-square that will be ideal. So this is just a summary of different measures of association. On this side, we have scale of the both variables and the measures of association needed. When both of them are nominal, like we are going to do now, that's categorical. When both of them are categorical, we do chi-square. When both of them are ordinal, like we've just finished doing now, we do Spearman's rule. When both of them are ratio scale or continuous variables, we do Pearson's correlation coefficient. We are not going to talk about this, but there are situations where one of the variable, possibly the independent variable, is continuous, and then the dependent variable is binary. These are variants. We do what we call a point serial correlation. Point serial. But this is the one we are talking about now. We have treated these two. So chi-square is primarily used to deal with categorical or frequency data. That is clear. The data that we analyze consists of frequencies. That is the number of individuals that are in categories. So in other words, the variables are measured on a nominal scale. You can see the measurement scale coming in now. So please, Very important. That types of variable and measurement scale is cardinal. If you don't get those two from beginning, there's nothing you can do about quantitative analysis. You'll be going at error. So that's why I keep emphasizing those two, measurement scale and types of variable. The test statistic for frequency data is called the Pearson chi-square. And the magnitude of that Pearson chi-square reflects the amount of discrepancy, that we have between observed frequencies and expected frequencies. And this is the formula for chi-square. That's the symbol for chi-square. It is the summation of the observed frequency minus expected frequency squared divided by expected frequency. If the observed and expected are very similar, our chi-square value is very small. That means the discrepancy is small. If they are very different, the chi-square value is large. If you want to know the magnitude of the difference, you could calculate the odds ratio, which we are going to do possibly in the 4th class, because I don't want to bring that into this class now. We are trying to build it step by step. Okay, so that's the same thing I was talking about.
We have 10 more minutes. We have 10 more minutes.
10 more minutes?
Yes.
Okay, so allow room for questions and...
Questions. Yes, sir.
Yeah.
Yes, sir.
Please permit me to make it 15.
Okay, sir.
Yes.
Okay, sir.
Yes, I started a bit late, if you remember. Sorry. So that's the same formula: observed minus expected squared divided by expected. And then we sum everything up. So if we have like a research question, maybe what is the association or relationship between one categorical variable and the other categorical variable. From your research question, you will determine the appropriate test, and we are assuming that for this particular situation now, we are using a chi-square. Then you establish your level of significance, that's your alpha level. It can be 0.05, it can be 0.01, it can be 0.001. You determine your p-value, that's the alpha. And then you formulate your hypothesis, the null and alternative hypothesis. You calculate the test statistic, and then you determine the degree of freedom. We are going to calculate this. And we compare our statistics with a critical value. So we are going to do like a sample classwork using the critical value. There's a table for chi-square values, and then we eventually look at outputs from SPSS. So we said that our chi-squared is used when both variables are on nominal scale or both are categorical. And sometimes you have ratio data that you can then categorize them. You can say above 40, below 40, you have already categorized, although the raw data were continuous. So you can now categorize, and then you can use chi-square. And it assumes that observations are randomly sampled from the population, and all observations are independent. These are some assumptions, that we have to fulfill. And like I told us, it doesn't make any assumption about the shape of the distribution, so it's a non-parametric test because they are categorical variable. They cannot have, a normal distribution. So our alpha, most of the time, this is the alpha that we work with. You have your hypothesis. There is no relationship between A and B. There is a relationship between A and B. And then the null hypothesis has been stated. The alternative has been stated, okay? Then you calculate it. And the calculation, we say that is the summation of observed minus expected frequency squared divided by expected frequency. So what we normally have from our data is observed frequency. Then we need to calculate what should be the expected frequency. And that's the formula for expected frequency, and it is just the frequency, the total frequency in the row times the total frequency in the column divided by the total number. And I will give you an example now to make what I've just said very clear. So that's the formula for our chi-squared, the summation of the observed minus expected squared divided by the expected, okay? This is the same thing with this. Is observed frequency, expected frequency. It's just the same thing. Okay, that's just what I just said. Observed frequency, expected, and chi-square. We determine our degree of freedom. How do we do that? Normally, your chi-square should be generated in a table. You have your row, and then you have your columns. So, for example, here I have 2 rows. This is 1, this is 2, and then I have 3 columns. So the formula for our degree of freedom in chi-square is the number of row minus 1 and times number of column minus 1. Once we have that class example, it's going to be easy. Once we have the value calculated for the chi-square, the next thing is go and check the chi-square table. we go and check the value of that particular chi-square, what it should be in the table. And this is our decision rule, and I don't want you to forget that. If our own calculated chi-square is greater than what we have in the table, then we reject the null hypothesis. But if it is not greater, we fail to reject the null hypothesis. So we have the critical tables values, they are standard, and I'm going to show an example. This is an example of the critical values of the chi-square distribution. That's how it comes out, that's how it looks with different p-values. So depending on the p-value that you choose, those are the p-values. And depending on the degrees of freedom of your calculation, you can now pick the particular value that you work with. So an example here, you as a researcher, you're interested in examining relationship between heart disease and COVID infection. And then you set your questionnaire for 90 elderly patients, and you also collect information about if they have heart disease, which is categorized present or absent, and then your COVID test shows negative, indeterminate, or not sure, and positive. So our heart disease is binary, and our COVID test is 3 levels, and both of them are categorical. And then you end up with a table like this. So for those with heart disease, there are 50 of them. Those without heart disease, there are 40 of them. The total is 90. So when you sort out all the findings, there are 10 people that had heart disease, but had negative COVID. 10 of them were not sure. 10 had a positive COVID, and that's how we arrived at 50. For the heart disease absent, those are the values for the different categories. So these ones in blue are what we observe from our own data collection. And like I told you, we will need to calculate the expected frequency. So here we have the row frequency, and here we have the column frequency. As you can see there, those are the column frequency, and they come handy if you are calculating our expected frequency. Our heart disease, like I said, is in 2 levels, that is nominal and binary. The COVID is in 3 levels. We have negative, indeterminate, and positive. Our p-value that we want to use for this test is 0.05. We have our hypothesis that there is no relationship between heart disease and COVID infection, and then there is a relationship. That's our hypothesis, and that's our study finding. The one in blue is our observed. Now, the next thing is to calculate our expected frequency. So FO is observed. How did we get 13.9 as expected? This is the formula. Expected means the row frequency, 50, times column frequency, 25, divided by total, 90. That's how we got 13.9. You do the same thing for this one, the row frequency, 25 here. For this one, the 30, the row frequency is still 50, and the column frequency is 40, divided by 90. So if you do it for all the 6 cells, you end up, with all those FEF, which is expected. That's just what I was talking about, For the one that was observed 15 is 40 times 25 divided by 90. So once we do that, that's how we have our expected frequency for all the cells. Remember this, the calculation for our chi-square formula. We have 6 cells, so you pick them one by one. Observed frequency minus expected frequency squared divided by expected. So let's go to the first cell. Let me just go up there. For this one now, it will be observed 10 minus 13.9 squared divided by 13.9. That is for this particular cell. You do it for this cell, for the 6 of them, and then you sum all your findings, which is what is done here. And our chi-square by that method is 11.03, as simple as that. The next thing is to look out for our degree of freedom. How many rows do we have? 2, 1 and 2. How many columns? 1, 2, 3. The total is not part of the rows and columns, please. So using our degree of freedom, we have 2 minus 1 times 3 minus 1, and we have 2. Remember, our alpha is 0.05. That's what we are working with. So that is there. We have 0.05 as and our degree of freedom is 2. So we can go to our table to check the value. That's the critical value. Okay, so our p-value is here. Our degree of freedom is 2. So our critical value is just 5.991. And then we calculated 11.03. This is the critical value. This is our own calculated value. And remember, if our own value is greater than the table value, we reject the null hypothesis. So invariably, our null hypothesis is rejected, and we are going to go with the alternative hypothesis, which says that there is a relationship between heart disease and COVID-19 among the elderly patients. That's the end of the analysis. So that's our finding, that's our solution, because our own calculated is greater than the table value. If you were to do it with SPSS or any other statistical software, this is what we have. And you can see that the value is even the same thing with what we got. And it's even giving us our degree of freedom and giving us the p-value that is less than 0.05. And by convention, we will reject our null hypothesis and go with the alternative hypothesis. So this is what you see in an SPSS or a statistical software analysis. And this is how we report it. You report your chi-square value, your degrees of freedom, and then your p-value, and then you are done. Okay? Now, this is where I'm just going to spend like 2 minutes to explain something here. This is also an output of a chi-square analysis, but you can see that there are many different results that you are having here. It's the same chi-square, but you can be reporting a variant of the chi-square. It says here that this is computed for a table, a 2x2 table, and then there's a B part here that says that one of the cells have expected count less than 5. One of the cells has expected count less than 5. Now look at this first bullet point. If you are doing a chi-square, and if expected count is less than 5 or equal to 5, and it's a 2x2 table, instead of picking the p-value of the normal p-value, you use the Fisher's exact p-value. Let me go over it again. You can, if you, by virtue of the narration under your chi-square analysis, that's where you pick the particular one. So if your expected count is less than 5 or equal to 5, and your categories and your columns and categories are 2x2, you use the Fisher's exact, that's p-value. But if you don't have all those narration, you just work with the normal p-value. And if your expected count is greater than 5, and you are doing a table that's less than 2x2, greater than 2x2, you use the normal chi-square. If your count is greater than 5, and your table is 2x2, you use the continuity correction p-value. So we have the continuity correction p-value here. But there is something, this is just for A-level students. All I'm trying to say is that for all of them, based on experience, if a p-value is less than 0.05, either for continuity, for Fisher's exact, for the normal p-value, it will still be less. If it is greater, it will be greater for all of them. But if you want to show us that you're an A student, then you can go that extra step by picking the particular p-value that's actually appropriate for the particular analysis. And you will get that by looking at the narration, excuse me, under your chi-square output. So that's how you will now report it. If, for example, you want to use the continuity corrected or you want to use the Fisher's exact. So what I'm trying to say is that by default, if you are writing a proposal, you cannot say that you are going to analyze your data using Fisher's exact. Fisher's exact is a modification that comes after analysis. You can't predict before analysis. So it's not something that I'm going to use continuity corrected chi-square. No, it is after you have done the analysis that you will now pick that particular value. So people will say Fisher's exact. You can't just use ab initio. I don't think so. It doesn't work like that because you can't predict your data. It is after the data has been entered and analyzed that you can now know if you have some cell less or some cell greater. So you just use the variant of chi-square. So both of them are variants of chi-square. There are situations where you have only one row, and we can also calculate a chi-square, and we call that particular chi-square test the goodness of fit. Goodness of fit. And this is an example. I have here that suppose we want to know how people in a particular area will vote in general, and we are asking them the questions. By the way, APC, PDP, and Labour are just political parties, for example, and we want to see what's really going on. So there are 60 people in the locality, I know, and we have our question where we have 20 people voting, 30 for APC, 30 for PDP, 10 for Labour. The question is, can PDP win the district? And we generate our alternative and null hypothesis. There is no association between how they will vote and PDP winning the district, or there is an association. We go on with our chi-square formula, generating our observed and expected. But in a goodness of fit test, our expected is usually the mean of the observation, because it's just one row. So we add all of them together, which is 60 divided by 3 categories. That gives us 20, 20, 20. And if we do observed minus expected squared divided by expected for the 3 of them, this is what we have. And it will give us a value. And that value is 10. And how did we get our degree of freedom as 2? We have row. Remember, degree of freedom, row minus 1, column minus 1. There's no column. So it's just going to be row minus 1, 3 minus 1. That gives us 2. And by default, I said our alpha level is 0.05 and degree of freedom 2. And I think this was the same value we got in the last example. So we can see here that our calculated chi-square is greater than the table chi-square. So we reject the null hypothesis, and then we go with the alternative hypothesis that says that PDP might win. So this is what I'm talking about. This is our p-value, and that's our degree of freedom. It's still the same thing. Okay. Now, for a last example, and it's going to be very fast because we have seen the basics. What do doctors do with their free time? Is it that they watch TV, they sleep, or they plan strike, or they play? And I've categorized them by gender. So we have doctors, male and female being one category, activity or what they do with their time being another category. Male and female is binary. We have only 2 here, but we have 4 here. And after populating our table, this is what we have. So the next thing is to state our alternative and null hypothesis. Is there a relationship between gender and what doctors do? That's the research question, and we can calculate our expected frequency. For example, for this particular one, is going to be 50 times 100 divided by 200. That's how we are going to get our expected for that particular one. This one is going to be 70 times 100 divided by 200, and on for all of them like we did in the previous slide. And if you do that, all these ones in parentheses are the expected frequency. Expected frequency. Our degree of freedom is row minus 1, column minus 1. Our row is 2. Our column is 4. So 2 minus 1, 1, 1 times 3. So our degree of freedom here is just 3. Let's just have that at the back of our mind. Okay? And then our p-value, like I said, by default, we work with 0.05. Degree of freedom 3. So our table value is 7.81. Have that at the back of our mind. So if we calculate our chi-square, we get 10.10. Our table value is 7.82. Our calculated is greater than the table value. So we reject null hypothesis. And we now say that there is a statistically significant relationship between gender and what the doctors do with their free time. And we can see that most doctors will sleep as male and most female doctors will plan strike. Remember, it's just hypothetical. So that's just our discussion. Then you look for other literature to support whatever you have found. Assumptions of chi-square is that we need at least normality, 5 of our expected frequency values. We need at least 5 for our expected frequency value, and we must include all responses, not just the ones that are positive. Note that the variables are independent or related, and that's what the test can be used for. But rather, as with t-test, which we are talking about next week, the observations or data points don't have a bearing one on the other. And to help with the last 2 assumptions, our total number n should be the total number of people that responded to our questionnaire. So in our next class, we'll be talking about t-test and analysis of variance, which is the next inferential statistics we'll be talking about. I don't know if we have some few minutes for me to talk about some sample analysis where we can calculate in correlation age, and BMI. Remember, I shared that data set with us last week, maybe age and income, that's for correlation. These are examples of research questions where you have your predictor variable as continuous, outcome variable as continuous. The light blue ones here is the predictor variable. The green one here are the outcome variable. That's an example. And for chi-square, we can also look at relationship between educational status, and hypertension. Both of them are categorical. However, educational status is ordinal. I hope you notice that. So in situation where you have one variable ordinal, one variable categorical, chi-square still stands, please. Chi-square still stands. You can use it for both of them. Okay? And even if both of them are ordinal, chi-square still works because they are still categorical. So if we have time, I might want to quickly do that. Can I use 5 minutes for that, please?
Okay, sir. We have about 20 minutes for questions, so maybe you can take 5 minutes.
This wouldn't be more than 5 minutes. I'm talking about the analysis, just for us to see how it looks. What's it called? How the analysis looks using SPSS. Because we have been working with the manual way, and then let's see how we can have an example of it done, using a software. I don't know if you can see my screen.
Yes, we can.
Beautiful. So I have here different variables. Like I said earlier on, age, BMI. I'm trying to remove this. It is blocking. Okay. BMI, lipid, stroke, hypertension, yes or no, educational level, income, BMI, doctor. Okay, so that particular example I gave in the chi-square class, where I spoke about the gender of doctors and the activity they do, I actually went as far as like generating the same data on this data sheet. I said there were 200 of them. So maybe I will even first start that as an example, doing that same chi-square we did, in the class using the data set here. So for me to do the chi-square analysis, I go to analyze, I go to my descriptive statistics because I want to do a cross tabulation, for the issue of what's it called, to see the number of rows, the number of column. So I go to gender of my doctors, I pick it, I put it in my rows, and then I go to the activities, I put it in my column. And then I look at my statistics here, and then chi-square. Normally by default, chi-square is not highlighted, but because I want to do a chi-square, I pick the chi-square, and then I click continue, and then I say okay. And then I'm going to share the outputs, what's it called? I'm going to share the output page, and I'm going to stay with the output page going forward so that I don't have to be going back and forth. And as you can see here, can you see the output page, please?
Yes.
Beautiful. So as you can see here, this is just similar to what we had in the class, where I have, the gender, the male and female, the number per activity, those who are planning strike, those who want to play, those who want to sleep, and those who want to watch TV. And then I have my row frequency here, and I have my column frequency here. And as you can see further down here, this was exactly what we got in the classwork. Our chi-square was 10.0, I think 1 or 0.2. And you can see the degree of freedom is here. And our p-value is 0.018, which is less than 0.05. So from here now, by default, I will just reject my null hypothesis, and then I go with my alternative hypothesis. As simple as that. Let me also go back to analyze, and then try and look at, this time around, I want to check between education and hypertension. So I pick education, which is ordinal. If you look at this particular place, you can see something like a small histogram here, something like a staircase. That is a sign that it is ordinal. I put education on my rows, and then I want to check it with hypertension. I want to look at, is there a relationship or association between educational level and hypertension? And I bring that to my column. Chi-square is already highlighted. Let me just confirm it's there. Okay, it's there. I say continue, and then I click OK. And then I have it generated here. There are 180 participants. So you can see educational level, none, primary, secondary, tertiary, and the values here. Had hypertension, those without hypertension, those with hypertension. And then you can see my chi-square here. And the value of my chi-square is 0.324. My degree of freedom is 3. That is obvious because I have 4 rows here. None, primary, secondary, tertiary. 4 minus 1, 3. Hypertension is 2. 2 minus 1, 1. 3 times 1, 3. That's how I got 3 here. And my p-value is close to 1. That means it's not significant. So I fail to reject my null hypothesis, and then I can conclude that there is no relationship between education and hypertension. Last example using chi-square, cross-tab. So here, instead of educational level, let me put stroke. I want to see if there's a relationship between stroke, yes or no, and hypertension. And my statistics is also at chi-square. I click continue, and I say okay. And sharp, you can see it's just 1 second and it's done. And this is the table. Presence or absence of stroke, presence or absence of hypertension, and you can see here it is very significant. I mean, logically, even with common sense, people that have hypertension, there's a correlation with stroke. And you can see my chi-square value here, 16.722, degree of freedom is 1. My p-value is 0.000, very significant. So there is definitely an association between, stroke and hypertension. Now, maybe an example on, correlation. Let me do correlation. And we are doing bivariate. So I want to correlate age. I have baseline age here, and I want to correlate it with income. Age, okay, let me start age and BMI. And as you can see, there's something like a ruler to show that they are measurement, they are continuous variables, And here I have chosen Pearson correlation because both of them are continuous variable. If they were ordinal variables, I will be choosing Spearman correlation or Kendall-Style-B, but the Spearman is the one I'm aware of. And my hypothesis is two-tailed by default. So I can just say, okay, and let's see what it comes out with. As you can see the correlation here. This one is age and age, so it's going to be empty. BMI and BMI is going to be empty. And my correlation value here is 0.269. My p-value is very significant. And so this one is moderately strong or weak, not moderate, it's weak strong because it's positive. There's no negative sign there. And then I'll just do another one, correlation, bivariate. Instead of using age and BMI, let me remove BMI and let me do age and income and see how it looks like. All the other values have been highlighted. I click OK, and then we have it here. As you can see here, this time around, my correlation is negative, minus 0.048 for my Pearson correlation, and my p-value is also greater than 0.05. So this is not significant. However, there is a negative, moderate negative correlation. That's how to interpret it. And then before I forget, I spoke about scatter plot. So I click on my graphs, I go to legacy dialog, and on legacy dialog, I just scroll down to scatter plot. I pick the simple scatter plot and I define. Here, okay, I already have my age here. For my y-axis, I have my income on my x-axis, and I just click OK. I wanted to see how it looks. And we can also do that. So that's an example of a scatter plot. And as you can see here, I cannot actually say if it is positive or negative, which is the delimitation of a scatter plot. But we can check to see if it has any benefits by putting a line of best fit. And how do I do that? I double click on that chart, and over here, I have what it says here, add fit line, for the chart. And once I do that, I can pick the one I want. I want a linear line and close, and you will see something here. You can see here a line is fairly negative because it's going down and it's looking like 0. But more importantly, this is what I want to show you. I don't know if you are seeing the coefficient of determination here. It's 0.002, So So invariably it's close to zero. So there was, or I can say there is little or no correlation between your age and the income. Just the last example, I go back to, what's it called? To legacy dialogues, and then I go to scatter plot again. And this time around, I want to do, what's it called? Maybe age and which other value can I do? Let me do age and BMI. Let me put it there, and let me just go through it again. And then it gives me another chart, you know, and let me just try and put that line to see if it's going to give me a better interpretation. I want that linear line, close here, close there. And then you can see here, the line goes from lower left to upper right, which is slightly positive. What I have here is actually the R squared, 0.072. Now there's something I want to bring out. This is baseline age and BMI. Our R squared is 0.072. Baseline age and BMI. This is the one. And age and BMI. If we are to pick our R value here and square it, we are going to have that R square value that we saw in that scatter plot. And then that's how we have that value. And by now, I'm sure you should be able to interpret the coefficient of determination. You should be able to interpret a correlation chart, a scatter plot. You should be able to interpret, you know, a chi-square analysis. Thank you very much for your time. I can now hear and entertain questions if there are.
Yeah.
Over to you, Dr. Lam.
Thank you very much. Thank you very much, sir. There are several questions already on the chat box. I'll just pick some of them because our time is fast spent. Just have 9 minutes more. So I'll start with the first one. The person is asking if we have a 2x2 table, will Pearson chi-square or McNemal or Fisher exact test be the same value? I think that has been addressed. You've shown it in the charts in the example.
Thank you.
The next one is, do you need to use all the ways of testing normality, or you have to pick one or two?
No,
Okay,
just
I think
one
Prof
or two.
answered that already. Okay. If you categorize, you answered that about if you categorize a continuous variable, can you use chi-square?
Yes.
Somebody's asking what X and Y means.
Okay,
It's
we've
just
discussed that in our last
I don't
class,
know if you want to speak to
dependent
that.
variable and independent variable. It's just a notation. It doesn't have to be
Thank you.
anything. It can be Y and W.
It's
It
just a
can be anything.
notation.
It's a notation.
So the next one is what do you put into consideration before determining what your alpha value will be?
Oh, good question. So you, in your literature review, because you are trying to compare your findings in future with other people's work, you try and compare with what they have also done. You know, that is for the choice of P. But by convention, it's like just like what everybody works with is 0.05. However, there are some kind of analysis, like when you are doing studies that have a very high risk rate, we tend to reduce the p-value to make it more strong, like 0.001 or 0.00001. For example, I heard that when they are testing aircraft for safety margin, their p-value is 0.0001. That's 1/1000. You know, because any little error, the damage is crazy. And when they are also testing drugs, like all these chemotherapeutic medications, you know, they also reduce the p-value so that the risk margin is very, very reduced. But by convention, you know, it's 0.005 and 0.005. Yeah, no, 0.05. That's 5%.
Yeah. Yeah. So someone is asking, can fail to reject null hypothesis be interpreted as accepting null hypothesis?
Yes. So that's what accepting the null hypothesis is, what we actually say. But scientifically, the ideal way to say it is we fail to reject, because you can't just accept. You are not really sure. It's just the finding. So we just say accept null hypothesis for literal level, and that's the kindergarten way. But as a scientist, the best way and the most accepted way is that you fail to reject the null hypothesis. Good question. Thank you.
Yeah. Someone is asking, why did we pick Pearson chi-square and not likelihood or linear sir, in the picture you showed earlier.
Okay, so that also I have not studied why that is for that. The ones I am aware of is the Pearson chi-square, the continuity ratio, the features exact. Those are the ones I have studied. There are so many things that is here to, we are just at the beginning level. At least that suffices for what we are doing.
Yeah.
That one can be, one can read it off. Yeah, one can read it off.
Yeah.
Except somebody has an
Okay, I
idea.
think it is said that likelihood is actually used when the sample size is very large, more than 1,000, it can suffice.
Beautiful, beautiful, beautiful.
But I don't know what linear stands for anyway. So somebody asking why p-value is 0.05.
It's by convention, like I have said earlier on. It's by convention.
Yeah, convention. Thank you, sir. But can you please how do you calculate or determine p-value for both correlation and chi-square analysis? You've given an example on the
Yes.
SPSS. Yeah. Does it matter which variable is put on the row or column?
Okay, yeah, it matters because there's part of logic. You know, like I was saying that the example I gave, does height, predict weight? It will be difficult to say does weight predict height because that's not logical. There must be a kind of temporal arrangement. You understand? So there are situations where both dependent and dependent don't matter. Anyone can be in any area. But in situations where you need to talk about, okay, I gave an example earlier on too about exercise and blood pressure. You cannot say does blood pressure predict exercise? It's not logical. So it has to be exercise as independent and blood pressure as dependent. So there's need for logic, and that logic comes from literature review also, from what people have done in the past.
Okay, thank you, sir. Somebody is asking that, so does it mean that when you are doing SPSS analysis, you're supposed to pick Fisher exact chi-square continuity test and determine which one you use after the result comes out?
No, you don't pick features exact. If you notice when I was doing the SPSS, all I clicked was chi-square. You understand? So it is when chi-square runs the analysis that it brings you those footnotes for you to know in case you want to pick the particular p-value. So if your analysis fulfills any of those particular footnotes, that's when you can now choose either the continuity likelihood ratio or you can choose the features exact. But like I said, it's just for advanced students. The truth is based on experience. If it is less than 0.05, all of them are less than 0.05. It is greater, all of them are greater. It's just for us to know that you really knew the particular value to pick. So I don't know where you choose ab initio. All I know is that you just choose chi-square, and chi-square gives you the variance after the analysis for you to choose the one that is most applicable.
Yeah, thank you, sir. I think two persons want to know about difference between one-tail and two-tail tests.
Okay, I don't know if we have time for that. It was part of the assumptions I had, before we started this class, that people will have understood hypothesis testing. We might find some time in the future to talk about that. Sincerely, there's not enough time to do that now. Except maybe on the platform, we can explain that on the platform. Yeah, on the WhatsApp platform might be ideal.
Okay, thank you, sir. Yeah, somebody gave an example here, which I skipped earlier. I gave an example of study objective and wants to know what type of test should be used. So says to assess the perceived stress on the performance and productivity of office professionals at EK, which type of test should be used?
So the first variable there is stress, and then the dependent variable, there are two. We have performance, perceived stress on the performance of whatever. So we have two variables. A is stress, or X is stress, Y is performance. Now, what test you will use depends on how you measure stress. Are you measuring it with a measurement instrument, or are you categorizing it, or are you putting it in ordinal or ascending order? So that's number one. The performance, is it a score? Is it a category, whatever? So you are the one that will know the particular measurement scale you are using for your independent variable and independent variable. If both of them are categorical, then we go for chi-square. If both of them are, what's it called? Continuous, then we go for correlation. Yeah, so that's how it goes. You must know your kind of variable and the kind of measurement scale. I can't overemphasize that sincerely. That's where many people miss it. You must know how you are measuring stress. Is there a particular cuff that you put in their hand that gives the stress measurement, in which case it is continuous? Or is there a particular questionnaire that you score, in which case it's continuous? So you know how you measure it and you know how to score it. And then likewise, performance. Is there a score? Is there an exam? Is there a test? Or is this something that is categorical? And then you will now know the particular test that is applicable.
Okay, so let me take the last question for the. Okay, it's 10 o'clock already.
So both of them are Likert scale. Then you go for Spearman's rank correlation.
Exactly.
Yeah.
Exactly. So I want to take the last question, which I think is important. Someone wants to know what is essential, what exactly is degree of freedom?
How do I explain that? Okay, so
or should we take to the WhatsApp page too? Okay,
I think we should go to the WhatsApp page so I don't take time. Well, I like that question. I'm putting it down. I will respond on the WhatsApp page. Degree of freedom.
Yes, that's why I picked it. It's actually upper. I brought it up because I think it's important. All right, so thank you very much, everyone, for. Go ahead, sir.
No, I've not seen anything.
Okay, yes. Thank you very much, sir, for this, again, another beautiful and interesting lecture. I'm sure many of our participants have gained a lot from this session, and I have also gained from this class. Like I said the last time, every of your class, I gained something new. Thanks a lot. I know there are a lot of questions that have not been answered. You can bring it to the WhatsApp group where we'll continue the conversation. I'll try and answer as much as I can, and I'm sure others will chime in to answer. Thank you very much. Do have a lovely weekend. Thanks, sir.
Thank you, Doc. Thank you, everyone.
All right, sir.